In section 8.1, we're just going to review some basic integration rules. Notice in the notes I refer to page 519 in the box. It's techniques for fitting integrand's basic integration rules. So for example, expanding, just multiply something out. Separating a numerator, instead of adding two fractions together, you split them back up. Completing the square, dividing improper rational functions, add or subtracting terms in the numerator, right? If you have a fraction with an expression like their example has 2x, but you need an extra term, say plus 2, so you add in a 2 and subtract out a 2. So you write 2x as 2x plus 2 minus 2. Using trigonometric identities and multiplying by a Pythagorean conjugate. So look at those techniques in the box, and you just put them in the back of your head, because once in a blue moon one will come up. Okay, let's do these examples in 8.1. I mean, all these you've done before. It's a review section. So the first example says evaluate the integral of 4x over x minus 8 dx. 4x over x plus. Okay. Now I think I'm going to do this one twice, so don't write large. You can write both solutions. I mentioned this in a previous video. I notice I have a rational function here, and the degree of the numerator is bigger than or equal to the degree of the denominator. And I mentioned one technique that sometimes gets you somewhere is to do long division. I'm not saying that's always going to help you, but I'm going to do that here. Okay? So let's do the long division. You could do this on scratch paper. I'll do it over here. So I need 4x divided by x minus 8. And you always write, when you do the long division with polynomials, always write from highest power to lowest power, from left to right. All right, so what do I have to multiply x by to get 4x? Well, I need a 4. And when I multiply 4 times x minus 8, I get 4x minus 32. But then I have to subtract, so I'm going to change the sign and add. And then when I add, I get 32. And again, how do you know when to stop in long division? When the degree of this is strictly less than the degree of that. So this is a constant, the degree is 0, that's degree 1, so we're done. Okay, so then how do you rewrite this? So what is 4x divided by x minus 8? Well, the quotient is 4 plus the remainder over the divisor. So 32 over x minus 8. Now I haven't integrated, all I did was do the long division. So 4x divided by x minus 8 is 4 plus the remainder over the divisor. Okay, now is this something we can integrate? I should have asked that right here before I did all that. Is that something we can just write down the answer to? And the answer is no, so we have to do something. Well, the integral of 4 is easy, that's 4x. Now, what about this? Well, the 32 is no problem. You can pull that out front, right? Plus 32. Not all the way out here, just the front of this one. Now, I'm left with 1 over x minus 8. Now, what's the integral of 1 over x minus 8? Well, if it were just 1 over x, that'd be easy. It's natural log absolute value of x, right? Right? So basically, I'm trying to argue, how do we integrate that? Well, you would do a substitution on this. You would let u be x minus 8, wouldn't you? But that's a linear substitution, so I don't really have to work it out, right? So if u were 1 over x minus 8, you're going to have a 1 over u, and that's just a natural log, okay? So this is going to be natural log absolute value of the linear. Now we have to adjust the slope, but the slope is 1, and 1 over 1 is 1, so I don't really have to do anything with that. And then plus. So again, I'll pull the 32 out. The integral of 1 over x minus 8, if you let u be x minus 8, that's a linear substitution. So if it were just 1 over x, the integral would be natural log absolute value of x. So the integral of 1 over linear is natural log absolute value of linear, but you adjust for the slope, which is just 1. So that one's actually not hard. I just wanted to remind you about the long division. Now what's another way we could have done this problem? All right, so I'm going back to the original problem here. Okay. We could have done that linear substitution to start with. Let u be x minus 8. Now, I can't just write down the answer because there's a little more involved. So you notice here when I did the linear substitution, the variable is only in one place. See, now it's in two. So I need to work this one out. So what's du? Du is dx. Okay, let's do the substitution. So instead of dx, I'm going to write du. Notice in the denominator, I just have u. Now, don't forget you have to substitute everywhere. I have an x in the numerator as well, so we have to write don't do mixed, don't have an integral of mixed variables, okay? So, well, the 4 is no problem, I can pull that up front. Now, what's x in terms of u? Well, if you solve for x here, add 8 to both sides, x is u plus 8. And you said, well, we still have a fraction, so why does that help? It helps because here, the denominator was a binomial, now it's a monomial, it's a single term. And whenever I have a fraction, a rational function with a single term in the denominator, especially if I'm trying to integrate, you can break it up. Okay? So u over u is 1, and then you have 8 over u. Now I'm not integrating, I'm just breaking that up. That's one of the things that was in the box, remember? It said separate numerators. Right? So I put u over u plus 8 over u. So I separated the numerators. Okay, so let's integrate here 4 times. Well, the integral of 1 is u. And then the 8's no problem, but just put that up front. And then the integral of 1 over u is natural log absolute value of u. Let's see. And now I have to go back to x's. U is x minus 8. Notice if I distribute that 4, you get 4x minus 32 plus 32 natural log absolute value of x minus 8 plus c. Now, is this the same thing we got over there? It should be the same thing. We have a 4x and a 32 natural log absolute value of x minus 8, but I've got an extra minus 32. Does that throw anything off? Well, no. That's the idea of the plus c, remember. 32 plus a constant is another constant. So they are the same answer. So there's 2 different ways you could have done that problem. Okay, but I really wanted to go through the long division again because a problem may not work that great the way we did here, especially if it's not a linear substitution. Okay, let's look at the next problem. It says evaluate the integral of x times 1 plus 1 over x cubed dx. Okay. Is this a straight integration problem? Could you just do this, without doing any kind of substitution? Sure. I mean, you could just multiply all that out, multiply by x, and integrate term by term. And of course, you don't want to do that unless you absolutely have to. But is there something reasonable to try for substitution? Well, if I let u, again, I'm just thinking out loud here. If u is 1 plus x to the minus 1, what's inside the parentheses, du is minus x to the minus 2 dx. Or if you want to rewrite that, minus 1 over x squared dx. And notice I don't have that anywhere. So that's not looking very promising, the substitution. I mean, maybe there's some trickery you could do, because I don't have a 1 over x squared. You could put in a 1 over x squared, but then you'd have to multiply by an x squared. And that'd give you an x cubed. So I don't think that's the way to go. So I think what you just need to do here is cube that out. Now you may remember in Calc 1, for pre-cal, the binomial theorem, how do you cube, well, how do you raise, any binomial to a positive integer power? Remember, you start with a cubed, or if that's 10th, you start with a to the 10th. The powers of a get smaller, the powers of b's get bigger, and then you just have your coefficients from Pascal's triangle. So again, if it's, you start with an a cubed, the next term is going to have an a squared b. The powers of a go down, the powers of b go up. Then you're going to have an ab squared, and then you're going to have a b cubed. And remember, the sum of the exponents is always that number right there. And then you get your coefficients from Pascal's triangle. Remember Pascal's triangle, you have a 1, 1, 1. And you always have a 1 on the ends, and then you get the number underneath by adding the ones above. So 1 plus 1 is 2. The next one will be 1, 3, 3, 1. And because this is a cube, this is the one used for cube. So it's 1, 3, 3, 1. So that's how you cube a binomial. Okay, so that's what I'm going to use here. Instead of multiplying 1 plus 1 over x 3 times, I'm just going to use the binomial theorem here. Okay, so my a is 1, and my b is 1 over x. Okay, so a cubed, well that's 1 cubed, that's 1, plus, and then I have a 3, and then it's a squared b. Well, a is 1 here. Let me just, a is 1, so let me just take that out. A is going to be 1. A is 1, okay. So I'll have 1 plus 3 times b, which is 1 over x, plus 3 times b squared, which is 1 over x squared, and then plus b cubed, which is 1 over x cubed. Okay. So now I'm just going to distribute the x, and x times 1 is x. X times 3 times 1 over x is just 3. And then I'll have a 3, an x cancels with an x in the denominator, I get 3 over x. And then x times 1 over x cubed is 1 over x squared, or x to the minus 2. So that's not so bad. I mean, the work there was just using binomial theorem. Do you understand why I wrote this one as a fraction and this one with the negative exponent? Because it's two different integration rules. Okay? Because remember, x to the minus 1, you don't add 1 to the power, divide by the power. That doesn't make any sense. That's why I wrote it this way, to remind me it's a different rule. So let's just integrate. The integral of x is x squared over 2. Integral of 3, 3x. This is 3 times 1 over x. That integral is 3 natural log absolute value of x. And in the integral of x to the minus 2, add 1 to the power, divide by the power, you get x to the minus 1 over minus 1, which is minus 1 over x. There we go. Okay, well that wasn't too bad. But notice I did think about using the substitution, but just because you want it to work doesn't mean it's going to work. Right? So it was just easier just to say, fine, I'll multiply it out. Now, if this had been 10th power, I think I might have hunted for something else a little harder. But okay, so the next one says, evaluate the integral of 1 over 9 plus 5x squared dx. Okay, is this straight integration? Could you just write down the problem, the answer right now? Well, some of you might could if you learned the formulas. Maybe you recognize what it is. This is related to the inverse tangent function. Remember, the derivative of arctangent x is 1 over 1 plus x squared. So it has that flavor, but it doesn't quite match. So I don't have that complicated integration formula memorized. But I know the basic one for the integral with arctangent, but I just modify and do a substitution, because then it's one less formula for me to memorize. So that's what I'm going to do here, is just get it to look like the basic arctan formula. But if you weren't thinking that far ahead, what about a substitution? If you let u be the denominator, du is going to be 10x, and you don't have an x in the numerator. So that substitution isn't really the way to go. Okay, so in my head, I'm trying to make it look like the arctangent. Remember, the integral of 1 over 1 plus x squared dx is arctan x. Okay, so I'm trying to make my integrand here look like this. Now, the first thing is I need a 1, not a 9. So the first thing I'm going to do is factor the 9 out of the denominator. And why 9? Because when I factor the 9 from the 9, I get my 1 plus. And that's what I need. Now there's no 9 to factor out of the 5, so it's just going to be 5/9 x squared. And again, always check your factoring by multiplying 9 times 1 is 9. 9 times 5/9 x squared is 5x squared. Okay, so that's the first thing. So I've got my 1. And then you want to write it as not x squared, but something squared. Okay, so I can pull the 1/9 all the way out front. And how do I write that 5/9 x squared as something squared? Okay. Oops, I'm getting ahead of myself. That's going to be square root of 5 over 3x, quantity squared. Because square root of 5 squared is 5, 3 squared is 9, x squared is x squared. Okay. So notice I have 1 over 1 plus something squared. So it would make sense, I mean it basically fits this form except for it's not an x, it's stuff. So it would make sense to let u be what I have in parentheses there. Let u be root 5 over 3x. So I'm doing a substitution now. Because notice if u is this, I'm going to get u squared right there. Now this is a linear substitution, so I don't really need to work it out. I'm going to go and work this one out, and then the next one I won't. But we could just use that linear substitution business I've been using. But let me just work this one out just because I haven't done one in a while. So let's take du. Well, that's a constant times x, so du is root 5 over 3 dx. And I don't have a root 5 over 3 in the problem, so I just want to get dx by itself. If I multiply both sides by the reciprocal, I get 3 over root 5 du is dx. Notice it's 1 over the slope. That's not a surprise. Okay, so let's do the substitution here. So I have my 1/9. Okay, instead of dx, I have 3 over root 5. 3 over root 5 du. So I replace dx with 3 over root 5 du. And all I have left is the integrand, and that's a u. So it's 1 over 1 plus u squared. And now we're ready to rock and roll. 3 cancels on the 9, so I get 1 over 3 root 5. And then the integral of 1 over 1 plus u squared du is arctan of u. And then you back substitute. And u was square root of 5 over 3x plus c. And there we go. So that one's not too bad either. Now again, I mean there's a formula, the integral of 1 over a plus bx squared, something like that. And you can just memorize. I don't have it memorized, I just do this. It's one less formula for me to memorize. Okay, so hopefully, since we've done some of these linear substitutions, you could see how to go directly from here to here. Okay, so you'd have the 1/9 out front. And then if this is u, you realize it's 1 over 1 plus u squared, so that's going to be arctan of u. And then you have to do 1 over the slope, which would be 3 over root 5. And so you could have gone straight from here to here. I just went ahead and worked it out, just to work it out. Okay, let's do another one. This is number 55, which says find the general solution of the differential equation 4 plus tan squared x y prime is secant squared x. Okay, you may have done some of these basic differential equation problems in Calc 1, but if not, let me tell you what a differential equation is, just in case you don't remember. Okay, a differential equation is an equation that may involve an independent variable, here x, a dependent variable, y, say, and one or more derivatives of y. So you have to have a derivative in your equation somewhere to make it a differential equation. So you may not have an x. I mean, you could have y prime equals y. Notice there's no x there. Okay, But you may have x's, you may have y's, and then you have to have some derivatives. I mean, you don't have to have an x or y, you could have y prime as 7. Okay? So there's no x, there's no y, but there's a derivative and a constant. Okay? Now, well, I mean, like, y is y prime. I think I had that one a second ago. What's a solution to this differential equation? A solution to a differential equation is the function y. You're trying to find a function that makes this true. What function is equal to its derivative? That's what that's asking. So e to the x, for example, y equals e to the x would be a solution. Y equals 0 would be a solution. Okay? So what we're trying to find in this problem is find a function y so that if you take the derivative of y and multiply by 4 plus tan squared x, you get secant squared x. That's what we're trying to do. So the solution is a function y. We're trying to find y. Well, they're trying to make this fancier than it is. I mean, if you solve for y prime by dividing, y prime is equal to this. So they're not making these, differential equation problems very fancy in their presentation. I mean, if y prime is that, what's y? It's the integral of that. Okay, so antiderivative of that. So that's all they're trying to do. They're trying to make it, fancy looking by writing it that way. Okay, so we're trying to find y. So we need to integrate secant squared x over 4 plus tan squared x. Oop, dx. Notation matters. Okay, so that's what we're trying to do. So that all this is an integration problem in disguise. Okay, so how do we integrate this? Certainly, boy, this is a mess. I can't just write down the answer from a formula we've already learned. What about a substitution? Well, the derivative of tan x is secant squared x. So just going blindly with that, I think I would let u be tan x. And then du is secant squared x dx. I mean, that looks reasonable to do because we can get rid of that secant square. And I don't have to adjust here because the du matches my problem. So if I do the substitution, du is secant squared x dx. And I'm left with 1 over 4 plus u squared, aren't I? Right? That's the du, and I'm left with 4 plus u squared. Boy, that looks a whole lot easier, a whole lot simpler than what we've had before. Okay, now what? Well, this is another arctan. So I'm just going to do what I did before. I need a 1 here. So let me factor out a 4 from the denominator. I'm left with 1 plus u squared over 4. Right, 4 plus u squared. Now I'm going to pull this 1/4 out front. And I want to rewrite this as 1 plus something squared. Whole thing squared. This is something squared over something. I want whole thing squared. Well, that's just u over 2, isn't it? Because u over 2 squared would be u squared over 4. Okay, so the logical thing to do here would be do a substitution, so let w be u over 2. But u over 2 is half u. That's a linear substitution. So I'm not going to work it out this time because I did it last time. Okay, so so this would be a linear substitution. If that were w, I'd have 1 over 1 plus w squared. That's just arctan. So I have this 1/4 out front. So I'm going to have arctan, or tan inverse, of u over 2. But you have to adjust for the slope, and notice the slope here is a half, so it's 1 over 1/2, which is 2. Don't forget your plus c. But we need to go back to x's. So I get 1/2 arctan, and u was tan x of tan x over 2 plus c. Right, I'm just replacing u with tangent. That's all I've done. So that's that one. Again, if this linear substitution is a little too complicated for you, you can always work it out, right? Just let w be u over 2 and go from there, just like we did on the last problem. Okay, so that should get you going on 8.1 for this just review of integration.